Okay, so I hope you guys enjoyed our genetic algorithm approach and are ready for some exciting homework problems coming up this week. It's going to have a lot of problems. I think with this problem it's going to have to be a double homework assignment. Many homeworks. So we're getting a little bit late in assigning, but you'll get all your homework problems, don't worry about it. Okay, who can tell me what is hashing? Anybody heard of hashing? Some people. What do you think it is?
Indexing mechanism to certify the database.
Okay, so hashing, not necessarily in a database. So hashing is a way to find something. Could be, you might be finding for something in a database, you may be finding something in a very large memory storage. You're trying to find something very, very fast. You want to find it, but you don't want to search for it. That's the great idea. You always want to find something, but you don't want to spend the time searching for it, right? You want to buy it, but you don't want to spend the time saving for it. So it's kind of a funny thing. How can we do this? So hashing is an idea that we're trying to improve linear search. Linear search means we search every one, and it could take us a long time if we have many things to search. Binary search can speed it up. It has a big O of log n, right? We have a sorted array, we go in the middle, cut in half. And then sometimes we have what we call a hierarchical index search. And we didn't really talk too much about this, but we'll come back to the B tree idea. What is a B tree and a B plus tree? But basically, then we can cut this down to maybe some number of levels. It's not exactly a constant, but we can try to do it. The hashing idea is we want to locate the data as a function of the data itself rather than searching and doing comparisons. So the ideal complexity of a computation in hashing is big O of 1, which is great. If you can do big O of 1, that means you can find something in constant time, no matter how many things you're looking through. You can just find it by function of the data itself. So, so let's look at an idea how we could do that. Let's say we are going to store 25 values or 25 keys. And the range of those keys are going to be between 0 for the minimum one and 999 is the maximum one. But we're only going to have 25 of them. So we have to store each of the keys in some place between 0 and 999, let's say in an array. So what we can do is we can say each hash table entry has a key field and a reference field. So the hash table entry, which is our array, is going to have two things in it. It will have a key field and a reference field. The key field will be what we're searching for. So if we're searching for a key of 50, and we look in this location, and it's a 50, then it's a match. One second. Turn off. Okay, so the hash table, which is basically an array or a table of storage, right, has two fields in it, the key field and the reference field. So if you're searching for a key of 50, and let's say the search space is very large, and so maybe the hashing function says, look over here. So you look over here, and the key is 50. That means what?
50.
It's a match. We're searching for 50. You look here, the key is 50. It's a match. And so therefore, because this entry has two values, it has a key and a reference, the second part of the match is going to tell you where to find it. So the idea of hashing is that you want to basically look at something, match it on the key, and then go where the reference tells you to find it. That's what we're talking about. So one thing we can do, we can take 1,000 locations, initialize our hash table to -1. That means we're not using -1, so this is invalid. So we know what we're not using because we're only going to use 25 out of 1,000. That's a very low utility, but 25 out of 1,000, what is that? 2.5%. Okay, so it's pretty low. So we'll start, so basically 2.5% means we are not using 97.5%. So 97.5% or 975 of these things are going to be net -1s. All of them are going to start off with -1s. Then we will store each key into location, so the key value is I, and we'll find out, we'll put it into hash table location I. So if the key is 50, we'll put key with 50 into location hash table 50. Very simple. So the hashing function says if you have a key of I, look into index I. Pretty easy. So now 25 of the 1,000 hash table records are valid, and the 975 are -1s, and we have something that's a hash function of I says just go look at index I. Okay? To see whether 123 is in a hash table, we simply compute h of 123, which returns 123, and we look into it. Okay. This is a messy slide. If the compare matches, the reference is correct. If the compare matches, then it's correct. If the field is -1, the reference is invalid. For example, let's say out of the 25 records that I put, I didn't put a record that said 575. So if I search for 575, hash function says look here, and I get a -1, well, it's not there. Because I can look for things that are not there, I have to be able to determine that they're actually not there. So you can imagine over here is that this is an example of a hash table. So down this column we have the keys, and down this column we have the references. And the references could be either addresses in memory, or they could be offsets in a very large file. Could be addresses in secondary memory, okay? Especially if we have many thousands or millions of things to search through. So notice that if we, so this is, let's say, index 0, 1, and then this is index 999. Notice that 999 is here, this is 123, this is 2. So that means that this value is 2, but 1 is not there. So if we get a 1 and we search here, it means it's not there. If we search over here and we get this value, it means it's not there. So some are going to be there, some are not going to be there. But we are going to waste 97.5% of the table. So our hashing satisfies the big O of 1 requirement, constant time. The hash table is inefficient. Okay. It's inefficient because we have this condition. Now suppose we had a set of employees in a company, and let's say the number of employees is 500. And let's say each one has a social security number. We're going to use a social security number to be the key, because we know that social security numbers are unique. At least we hope so. Okay, so each one has 9 digits, so the hash table must have 10 to the 9th key locations. But that's a billion. That's a billion locations. So now we only have 500 employees. That means 1 billion minus 500 over a billion is going to be the percentage of waste. So now our wasting is 0.99999 and increasing, right? So, but that would guarantee us that everybody has their own special spot, and if it's -1, it's not there. If it's not, it's there. So the wasting would be this is the wasting percentage. The utility would be 0.000000005. Very small. So imagine if it was just 0.999. That's like having a room and living in it, but the house has 1,000 rooms. It's a mansion, but you only live in one room. That's a big waste, right? Or lighting up the entire 1,000 rooms, but only living in one room. Doesn't make any sense, does it, right? So it's a wasting of resources. Okay, so the idea is we want to have big O of 1 for the locating of the keys, but we don't want to have a slot or a space in the hash table dedicated to every single key. Because here, in this approach, we would have to have a slot for every single 1 billion social security numbers. But we only have 500 people. Even the United States doesn't have 1 billion people, right? We're not even halfway to that. So it's a little bit too much. So to improve the approach, what we're going to do is we're going to reduce the amount of hash table locations to be equal to that of the actual number of keys. So for example, if I have 500 employees, it might make sense to reduce from 1 billion down to 500. That might be a reasonable thing to do. So now we're wasting 0 instead of wasting so much. So if we do that, then we now in the case of the 25 unique keys, we could create a hash table of 25 locations, and now the hash function cannot be hi is equal to I, because now social security number could be 135242215. But we don't have a slot with that. So now we have to map it to one of the 500 slots that we have for our employees. Okay. So if we, so basically what we would have to do is we would have to do something like have the hash function take the value of the social security number and maybe do modulo of 500 instead of 25, because 25 was the other example. If we did modulo of 500, that would return values remainder over 500, divide remainder over 500 would leave you a remainder between 0 and 499. And that would be proper indexing for 500 locations. So that would return something if we did 500, 0 through 499 range. And so the example of the new hash table might look something like this. So you can see that employee 500 is at this reference. That's where you can find them. Employee, let's say 52, 129, etc. So this is how it's going to work in this case. Okay, now, so that's an advantage that we can share fewer locations or allocate fewer locations, but we can have problems when a key is passed to the hashing function, returns an index which was returned by a previous key. For example, if we have a function h, which is I modulo 25, then I get h modulo 273 would give me 23. Because 25, right, goes into this certain number of times, and then the remainder of that is going to be 23. But also, h of 73 is also going to give me a remainder of 23 because 25 goes twice, and the remainder is 23. So if I'm putting those two keys, because they don't have a dedicated slot, they might go to the same location. And if I try to put them in the same location, I'm going to find out that when I go there, I don't have a -1 there, which means something's already in there, which means I have a collision. A collision. So a collision means that two keys try to go to the same slot. Now, that's a bad thing, but it's not the end of the world. It's a bad thing because we have contention for that slot in the hash table, but it's not the end of the world because it just happens. That will happen. In fact, it will happen more often than you think. You will be surprised how often it happens. Especially when the size of the hash table is close to the size of the data you're putting into the hash table, you're going to tend to get a lot of collisions. You will get fewer collisions if you start increasing the size of the hash table relative to the size of data. If you double the size of the hash table and you randomly map to it using a hashing function, you will not eliminate collisions, but you will reduce them substantially. If you make it 10 times bigger than the data, then you will reduce collisions even more, but the question becomes, when do you stop? Because we can try to make it so that the number of collisions is going towards 0, but then the size of the table is going to be growing so much bigger. And the point being is that as you have the number of collisions up here, the expected number of collisions up here, and then let's say you double the size of the table, you might have the percentage of collisions go down like this. But then when you keep enlarging the table, you get very small gain. So you and as you go to the right, you're wasting space. As you go down, you're getting better at not colliding, but if you're not colliding is going so slowly and your space is going so quickly, you have to get to a point where basically you have kind of, we call this a sweet spot. Sweet spot. Yeah. Think of your tastiest sweet dessert, and that's a sweet spot. Sweet spot is basically, we find the best trade-off. Make it bigger than the data, but not too big. So that making it any bigger would give you a smaller benefit. Sweet spot. Okay. So actually, it turns out that there's a whole set of keys which will map to the same hash table location. In fact, anytime you have 25 times any integer I plus 23, all those will give me a remainder of 23. That includes, where basically I could be all these different values. So I is 0, you're going to have 23 maps to 23, because 23 modulo 25 is 23. 1 times 25 plus 23, right? That's going to be 48. That's going to map to 23. All of these are going to map to 43. And so there are 40 of them that are going to do that. Okay. So we typically are going to create a storage mechanism. And you guys have heard of hashing, because basically, how many of you have used something like a hash map in programming. So have you had a hash map? Okay, so if you use a hash map, guess what they do? They use hashing. What's their hashing function? It's secret. Top secret, but we know kind of what it is. We're gonna find out what it is. Okay, so now, what happens when we do in fact have the collisions? When we have collisions, we have to do something about it. For example, let's say I have a key, and that key basically hashes to here. So I put it here, and then I put other keys different places, but then I get another key, and this one also collides here. So now I have to decide where I'm going to put it. Well, if the hash table is not full, then I'm going to try to maybe look here. Is this available? No. Somebody else is here. How about here? Yes. Puts here. So now we have resolved the collision. So next time when I'm looking for this, I'm still going to hash here, and I'm going to have to look for it. So it's going to so when it takes me more time to store something, it will take me more time to find it. So that's called linear probing. Linear because you're just going linear sequence. Okay. All right. Okay, so how can we improve hashing performance? We already kind of have an idea. We can increase our table or our hash table capacity, make it bigger. The bigger area you have to shoot, the more likely it's going to be free, because you have more probability, right? Especially you want your hashing function mapping in such a way that every single slot has the equal probability of being selected. So if you increase it from 10 to 1,000, and somebody's already in there, one of them is in there, the probability of colliding is going to be only 1 out of 1,000. But if you have 10 slots, it's going to be 1 out of 10. So clearly making the hash table bigger lowers the probability of a collision. We can also try to resolve collisions in a different way. Well, what do we mean by resolving collisions in a different way? Well, there are different ways to resolve collisions. So one technique we talked about is if we have a collision, we go to linear probing, try to find the first slot. But what if you just keep looking, the end, and you got to come to the beginning. Boop. So now when you're looking for it, collide, it's going to take you a long time to find it. Another technique would be something that's called quadratic probing. Quadratic probing means that we go 2 to the 0 power. Well, actually, I guess we square it. So it's going to be, 1 squared. It's going to be, so we're going to go +1? No, -1. Now we're going to go 1 squared, we're going to 2 squared, it's going to be 4 this way, 4 this way, 9 this way, 9 this way. So we try, and the reason we do that is because if we're going to tend to collide in this area, we don't want to muck up this area so much, so we're going to try to go further away by doing quadratic probing. So we don't make one area of the table too congested with records. Another way of handling it, so there are many different ways of handling it. Another very simple way of handling it is you have your hash table, and what happens is you have a collision. But you don't expect a lot of collisions. How do you know that? Because you've studied some statistics and you've taken Professor Dichter's class, which shows you how you can minimize and even count the expectation of collisions and how many you're going to have, et cetera, et cetera. So you allocate a second location for them. This one is not a hash table. This is just a linear table. So what happens is if you collide, you basically go to find, just add it to this extra overflow table. Overflow is anything that collides goes to the overflow. So if I have 1,000 records and 50 of them collide, then 50 of them are in the overflow. So then if I don't find it immediately, I go to the overflow and I have a linear overflow cost. So if the overflow is very small relative to the full data, it's not that expensive to try to find it. If your hashing function is horrible, returns 25, then everybody goes here, everybody goes to the overflow. You'd have to be pretty bad to do that, but it can happen, I suppose. So overflow area is another way of resolving collisions. But there are other ways of dealing with collisions, and we're going to learn how to do those later on. Okay? Or sometimes we can use a different hashing function. Or perhaps we should think about how big our hashing function should be relative to our data size. Okay? All right. So increasing the table capacity definitely can have the effect of reducing the collisions, but it will not eliminate it. You can't guarantee elimination completely of collisions. A table with 365 locations and a random 23 keys has a chance higher than 50% of at least one collision to occur. Did you know that? Well, we talked about that already in class. It's called the birthday paradox.
There is a birthday, 12 months.
Because your birthday are random days out of 365. So if you have 365 table and 23, your probability of one collision is about 50%. You see what I'm saying? So you can see that's a problem. And you can see the birthday paradox is just not a crazy idea. It has some reason to be discussed. So that's very significant. So imagine what would happen if we had 365 slots in a hash table and 200 values. You can imagine there's going to be a lot of birthdays in common. Some birthdays won't occur at all. All right, so that's scary. So we need a little more analysis to be successful in this. Now, we talk about something called the packing density. Let's make sure you understand what is packing density. It's a very simple concept. If I have a table that has this capacity, and it's empty right now, and then I fill the table of all the data I'm going to fill with. So this is how big the table is. The amount of data I'm going to put in there is like this much, but it's going to go randomly into it. So effectively speaking, since I'm taking this much space and I'm only putting this much data in here, this part of the table, or this much of the table, is going to be empty. So the packing density is the ratio of the amount of space used in the hash table divided by total space in the hash table. So for example, if I have 100 slots in my hash table and I put in 80 records into it, I hash 80 records into it, what's my packing density? 80%. And if I have 100 slots and I put in 50 records, 50%. So basically, what do you think happens to collisions, the expectation of a collision, when the packing density decreases? It goes down. And when the packing density increases, the collisions goes down. And what is the maximum packing density we can have? 100%. We cannot do any more using standard hash table, because hash table has only so many openings. So if you use them all, your packing density is 100%. So that's an important idea. So the idea is we should make the hash table larger than the number of keys, and the packing density of typically around 60% to 80% is considered to be the sweet spot. So if you said 70%, I'm not going to disagree with you. What's better for collision, 60 or 80? 60. What's better for saving memory, 60 or 80?
80.
Okay, so now we got to find that little thing, right? And of course, so it may depend on if memory is cheap and collisions are devastating, then you might go to 60 or maybe even 55 or 50 if you can afford it, because that will make your life happier. All right? Now, another technique of handling collisions is expecting them to happen. Expecting them to happen. So basically, if you expect collisions to happen, what we can do is we can basically allow multiple keys to go into the same location, but we can't physically fit them into a table. So what we'll do is, instead of having a table, we'll have basically just a table, and the table will simply have a pointer to where is the key and the reference, key reference. So create a linked list. So if we take a key and the hash table says, look over here, we get access to a list. And this list will point to all of the keys that hash to that location. Now, if we have, at this point, the idea of packing density doesn't make as much sense anymore, because now we're talking about hashing with chaining. So what we have is, we have a hash table, but not storing data, it's storing chains, which point to the data. So now if I have 100 records and 100 chains, 2 of them colliding to one place, or 3 of them colliding to one place is not a big deal. Because basically it means that on average, instead of big O of 1, I'm going to get big O of 3, which is equal to big O of 1. So that's still constant time, as long as I can be sure that statistically I'm going to get an expectation of single digits, or 2 or 3 or 4 expected records at that location. Does that make sense? So no longer can we talk about the packing density. Packing density is more appropriate for a hash table that's storing the data directly. Once we have chains, it's a little bit different. So chaining is a way to expect collisions and handle them like that. So with a hash table of n chains, we have a set possibly of n chains. We can do that easily, and it's not a big problem. Now, you can see it's going to be a big problem with standard hashing, because if we have a 365 and 365, you know it's going to be a lot of colliding. You could have 10 people having the same birthday. So insertion, deletion, and search requires a linear search of the chain. You hash the hash table, you follow the chain, and you search for what you're looking for, or what you're looking for to add, delete, or return. Another approach we talked about is the quadratic probing, so that's already something we did. We basically do k is going 1, 2, 3, and it's going to be +1, -1, plus 4, -4, plus 9, -9. Quadratic probing, this is going back to ordinary chaining, so I don't know why I have it in there. It's a mistake. I should move that slide someplace else, right? Next class. So I am going to look at this small analysis. So what I want to do is I want to find out what is the expected behavior, what is my average behavior of an algorithm implementing hashing with chain. So what I'm going to do is I'm going to assume that I have a hash table with m locations, so notice that's 1 to m, and I have n entries, where n could be less than m, could be equal to m, or could be greater than n, m, or even much greater than m, because chains can handle it, right? So we will assume, so what we're going to do is we're going to basically target one of these m chains. But we're going to assume that the probability is equally likely that a hashing function will determine any one of these chains, giving them the same probability 1 over m. And then each of these chains will have a length. So chain 0 will have a length 0. Chain 1, this one, so all of them will have this length. Okay. So the question is, what is the average complexity of insertion at the back of a list? And the back of the list is at the end of the list. As you start, you have the front, and then at the when you finish, you're at the end of the list. So how can you insert at the back of a list? Well, the first thing you have to do if you want to insert at the end of a list, you have to hash, get to the list. Then you have to traverse the list, and you have to make sure that every key you look at in the list is not equal to what you are putting in, because you want to make sure that your key is unique. Okay? You want to make sure your key is unique. So therefore, we will count that number of operations. So basically what we're going to do is we're going to say the average cost of inserting nth element to the back end of a list is the sum as I goes from 0 to m minus 1, all of the lists, times the probability of that list being selected, times the time complexity of traversing that list. So PITI. So this looks very familiar, right? So we know that PI is 1 over m, so 1 over m can come out of the sum, because the sum is going for I, and 1 over m is a constant with respect to that. And that's going to be 1 over m times the sum from 0 to m minus 1 of the length of list I, because that's the time complexity to traverse the list, is the length of list I. Now, I don't know what is the length of list I, but I do know that the sum of all the lists from 0 to m minus 1 of list I is equal to n, because I have n elements in the list. So therefore, my complexity is going to be n over m. N over m. Okay, so now let's do some thinking about what n and m might be. If the number of lists is approximately equal to the number of elements in the total hash table, then our average complexity would be big O of 1, because m over n will be just 1. even if the number of lists, for example, if m, for example, was half of this, m was half of n, then it would still be big O of 2, which is still big O of 1. So we have a very interesting result here. So what it's showing us that hashing of chaining, as long as we can guarantee that our probability of selecting a list is random, equally likely, then we can guarantee that our performance is going to be constant time. So that's a good idea. Now, what about the average of an unsuccessful retrieval? Well, unsuccessful retrieval has me first compute the list, then I have to traverse the list, and I have to check every single element, and I fail every single time. No matter how many I have, I fail. By the way, let me just go back to here. So when I say average complexity is constant time, it doesn't mean that it's always going to be one operation. It could be 2, 3, 4, right? Because this is big O. And so this is just an approximate value here. So therefore, this is the average. It doesn't mean it's the worst case. We're looking at the average behavior. Okay, so if we're going to have an unsuccessful retrieval, basically we fail to find the list returned by the hashing function. Every list is equally likely, so therefore our analysis is exactly the same. Exactly the same. So our cost of unsuccessful retrieval is still going to be big O of 1, which you can say theta 1 also. But I think if you say big O of 1, you're not worried about it because it means that it's constant time or less. I don't know how much less you want. So big O of 1 and theta of 1 are almost the same, right? Because there's nothing meaningfully less than constant time. All right, so let's look at the probability of the expectation of the average complexity of a successful retrieval. Let's think about what a successful retrieval means. So a successful retrieval means that I compute the list, I go to the list, I compare the first key, I may or may not match it. I compare the second key in the list, I may or may not match it. But before I compare the last one, or at the last one, I will match it, and that's what a successful retrieval is. So if we insert all the keys, as we did, at the back of the list, then the complexity of a successful retrieval is one more than the insert. If we insert the keys at the back of the list, then the complexity of a successful retrieval is one more than the insert. You understand why? Because as we are inserting it, let's say the list has 2 elements in it. If I'm inserting one successfully, that means I compare, I insert. How many times did I compare? 2. Because there's only 2 in the list. But once I search for it successfully, I get the list, I compare, miss, succeed. That's a successful retrieval. Okay, so in that case, we were saying that the complexity of a successful retrieval is one more compare than the same insert for that same element. So we'll consider the jth entry into the hash table. So this is the jth element. So that if the jth element means that I already in the hash table have j minus 1 elements. So now the jth element is coming in. So when I'm putting in the jth element, the average cost of the insertion is going to be j minus 1 over m comparisons. Because if I'm adding the jth entry, that means the j minus 1 entries are in the hash table, and they are distributed with equal probability across m locations. So on average, each chain is going to have j minus 1 over m entries. So that's my average cost of insertion. So because, okay, so now what I'm going to do is I'm going to be doing successful retrieval, so it's going to be j minus 1 over m plus 1. That's the additional comparison, right? So that's my successful retrieval cost. So the average of all possible successful retrievals is going to be the a of n is going to be 1 over n times the sum as j goes from 1 to n. So now what I'm going to do is I'm going to be retrieving every single element. Every single element. I'm going to be retrieving the first element, the second element, the third element, and finally the nth element, and I'm going to divide it by 1 over n to get the average retrieval. And so therefore, the jth retrieval will be the jth retrieval across all n possibilities. And that's why we're summing from 1 to n. So we have j minus 1 over m plus 1. So what we have is we have 1 over m, but we can also take out the over m here, and that's going to be 1 over mn times the summation. J goes from 1 to n, j minus 1 plus 1. So we can note this condition to be true, and so we have n minus 1 divided by 2m plus 1, which is still theta of 1 if m is close to n. Okay. And a successful deletion rather is the same as the retrieval, because we have to go and match it before deleting it. Okay. Now, what we've been talking about, everything that we've mentioned today, basically in terms of hashing, can be put under one umbrella, and that is static hashing. And static hashing just means one thing. It means that the size of the hash table is fixed. Static hashing, that's the only thing it means. So that means chaining is static. Ordinary is static. Ordinary with overflow, static. Because basically the hash table is fixed. And we haven't talked about anything but that, but we will look down the line, we will look at something called extendable hashing. That's a kind of algorithm where the hash table itself changes dramatically. Like you could have 10,000 locations and all of a sudden go to 57 million locations. And then go to 25,000 locations, then go to 850 million locations. And you still have to maintain the hashing without having to recreate the table. If you think about it, if you have a hash table with a packing density of, let's say, 70%, and you start putting more data in it, more data in it, more data, what's going on? This thing is going crazy. Now you're really colliding like crazy. So one approach might be, okay, just allocate a table, let's say, 40% bigger, and go through every value and rehash it. But that has the time complexity of linear, right? You got to go through everybody, you got to rehash everything into a large space, you have to delete the space. It's extremely inefficient. So that's not a good solution for a dynamic hashing. So the dynamic hashing is extendable hashing. It's slightly a different approach. Another possibility for hashing is something called bucketing. I don't have a good slide for that, but I'll explain to you how it works. Bucketing. Like a bucket. You know, a bucket list, you know that? See that movie? No. All right, so a bucket is a pail, right? And so a bucket basically is, rather than having a hash table that has only slots for a single record, we have a hash table which is composed of buckets. And a bucket basically is able to hold multiple records. So when you take a key and you hash it to an index, it doesn't hash to a location in a hash table with a single entry, it hashes to a bucket with multiple entries. So for example, if a bucket has a capacity of 4, that means the first 4 records that are going to go into that location will not be colliding records. They will just go into the bucket. So if your probability of having 5 records hashing to a location is extremely small, that means 6 is going to be even smaller, 7 is going to, forget about it, it's not going to happen. What's going to happen is that you'll have very few records that actually are the 5th record or the 6th record coming in. It'll be very rare. And you can handle them how? Overflow is probably a good idea. Now, the advantage is you have lower probability of collision. What's the disadvantage?
Extra memory.
Memory.
Extra memory.
So, go ahead.
Memory. Extra memory.
Okay, memory? Okay, because now, even though you have some buckets that have 4 in it,
Some might not
more have probably 3, 2, 1, and 0. So now you are wasting a lot of memory potentially, and again, we can calculate these things, what our expectation is. So there's always a trade-off. It's always a trade-off. Okay, extendable hashing we're not going to talk about until different time, so we'll save that excitement for you later. All right. All right, so let's look at some probabilities. Probabilities are actually, these are not probabilities, these are just hashing functions. So this is just some idea of how you can produce hashing functions. Okay, if you're using something like some standard data structure like Java or C# and you're using a hash table or hash map or something like that, then it's automatically going to give you something like that. Sometimes they call it a map, sometimes they call it a dictionary, sometimes they call it a hash table. It's all the same thing. Key value. Key determines the location, value is what you store at that location. Or it could be key reference if you're using a database. Then the reference could be, for example, location in a file. But for internal memory, then we're really talking about key value. Okay, so one of the things we can do is for example, how do we find out a hashing value for these? Well, one of the things we can basically take something like the first character of the person's name, which is 74, and then multiply it by the ASCII value of the second character. And that gives you a relatively interesting number, right? And then what I'm going to do is I'm going to do a division divided by 1,000 and take the remainder. Notice that I get these different values for different people. That's one possibility. What makes a good hashing algorithm? We want one that has a key map to any location of the hash table with equal probability. That's what makes it good. Was our previous example, why is our previous example not a good hashing algorithm? Why is it not good? Well, it looks good here, because I fooled you, but yeah, so you can see basically, now if we have Joseph, John, and Joanne, they're all going to go to the same location because I'm only taking the first two characters. So that's probably not the best algorithm ever. Oh, I expected it to be too great, I did 4 examples. Okay, you should consider more names. Okay, take a book of names and run the 3 algorithms, see what you get. Okay, so we talked about this. Skip that, okay. Okay, so these are going to be some algorithms how to produce hashing functions. This is called the general folding and adding algorithm. These are very, very simple. So let's say you have Joseph and Melvin, right? So notice what we can do. What are these? These are just ASCII values, right? And then we have John here. So in this case, we have some blanks, and we can use a 32 here for blanks. Or perhaps we just start using the last name. And if we run on the last name, we read a city or something, you know. We use something, so we want to kind of look, you know, these 32s are not very good because if a lot of people have 32s, they're going to create a lot of sameness towards the tail end. And so what we can do is we can do things like folding and adding. If you take a look at a name like Joseph, notice that we have 74 and 111, and basically we're just going to fold it. So 7 and fold it with 111, it becomes 74,111. Now that's an unexpected thing to do, right? And 115 plus 101 has 115,011. So add these numbers together, and you're going to come up with 301,316. Who would have known that we would have had that number from Joseph alone? Okay, another possible thing we can do is we can take each of those numbers and do a modulo by 19,937, because it happens to be a large prime number, add it to the prime modulo of the second one and the third one, like that. And then take the whole thing, and then maybe take the modulo of 19,937 again, and then you can do a modulo of whatever you want to do in your table. So you're going to try to really randomize the value. So typically we divide by large prime numbers, which tends to produce a better distribution. We tend not to divide by numbers like 100. Because what it's going to have to do, what it will tend to do is tend to hit some locations more than others. We don't like that. So we want prime. There's no common factors. So we want to divide it by a large prime number. Okay, so in this example, if our desired number of slots is about 100, then a good choice would be 101. Why 101? Because 100 for a table size is not a good one to do modulo over 100, but 101 is better. Why? Because it's prime. So if you find that with your packing density, let's say you want to store, so this is a good test question, it's not very hard. Let's say you want to store 6,000 records with a 60% packing density. How big should your table be? Well, you're going to take 6,000 divided by 0.60. That will give you the nominal number of slots that you need. And then what you want to do is you want to take the next prime number bigger than that. Which one is it? I don't know. Do I expect you to know? Absolutely not. But just write it for me. The next prime number bigger than this. So if I give you a multiple choice test like I did last time, which you loved so much, you can say it's the prime number bigger than this. I can say prime number less than that. And I give you some bad choices, I give you a reasonable choice. Okay. Don't worry, the final exam has to be easier because you guys did so badly on the midterm. So I have to make it very easy. One question.
Yes, sir.
What is your favorite professor for algorithm? Everybody can go. And if you get a 0 on that, you deserve a 0. All right. No, but it's not going to be that easy. But it's going to be easier because I want to make sure that you guys can but study just as hard.
Yeah.
Okay. All right. So now we talked about hashing. Basically, remember when we talked about initially if we had, for example, 25 employees with 500 slots, and we just gave everybody a unique number. That's called perfect hashing. H of I is equal to I. It's perfect hashing. It's not very normal to do that because you'd have to have too many possible slots. So that's optimal. It's also called perfect hashing. Typically, most keys map to unique hash table slots, but some do collide. We call those synonyms. Okay, they're different keys, but they want to go to the same location. The worst is all keys are going to map to the same slot. You have to be extra poor programmer to do that. Forget to code the function and return 0. Everybody goes to the same. A realistic worst is all keys map to a subset. So all multiples of 25 get hit, but nothing else in between gets hit. Very bad. To avoid poor distributions, be aware of the expectations of the set of keys you're likely to see. So expectation, probability, all that kind of stuff. You should simulate your hashing function with the test data. So if you're going to use names, get a set of names that exist, real names, English names, Indian names, French names, Russian names, German names, Polish names, Spanish names. And try to generate some random data, put them together and see what you're, so that you can do a sort of simulation. As an example, a hash table of 10,000 slots can store 8,000 employees, hashed by the first letter of the last name. So all employees would hash to 26 of the 10,000 slots. That's very bad. Although we have many slots, many of them would be empty, right? Others, such as J, would be receiving more than 1/26 of the total key set because there are more people named with the J letter than they are with the Z letter. Although, that may not be true if you're writing an application in China, because Z and X are very popular letters in China for last name. Not so much for American names. Okay, so other type of strategies, so look at this over here. So these are just some crazy ideas you can come up with. So let's say you have the original key right here, and what you can do is you can square the key. The hash function squares the key and retrieves some number of digits from inside the number. So you take this number, you square it, and you extract the 3rd, 4th, and 5th digit. And then you get this. So this is another interesting idea, and of course you can do a combination of different things. You can also do a radix transformation. Radix is the base, right? So radix transformation means, for example, if the key is in base 10, the base 8 value is 2, 3, 4, 5, for example. So that gives you more digits, which is kind of interesting. You understand how to go to base 8, right? I'm not going to test you on that, but you get the idea. So then we can take the octal key mod 101, and so in that case I get some crazy numbers. And 101 would be a table of size 101, 0 to 100, and that would be a nice prime number for us. Okay, so now we're going to get into some interesting statistical analysis. We're going to assume, so this is the assumption that we're going to take. We assume that we have a total of n slots in the hash table. So we're just going to assume a linear hash table of slots. We assume that we have hashed all the keys into the table using a hashing function. Now, we're going to assume that our hashing function is a good one, meaning that every slot has an equal probability of being selected by the hashing function. So the probability y is the probability that the hash table slot is chosen, and the probability n is the probability that the hash table slot is not chosen. So the probability of y is 1 over n because it's a good hashing function. The probability of no is 1 minus 1 over n, which is n minus 1 over n. So if you have 101 slots, it would be 1 over 101, and this would be 100 over 101. So 1 over 101 is about 1%, a little bit less than 1%, and 100 over 101 is just about 1%, just about 99%. Okay, so the probability that two keys hash to a given slot. So you take a slot, and you're going to have a key hash to it. What's the probability that two keys are going to hash to a given slot? Well, the probability that the first one comes into the slot is going to be 1 over n. So I have a hash table, I'm picking this slot. What's the probability this key goes here? 1 over n. And the second one comes in, what's the probability it hits the same slot? 1 over n. So the probability of both of them hitting the same slot is going to be 1 over n squared. So if n is equal to 100, it's going to be 1 over 100 times 1 over 100, which is going to be 1 over 10,000. 0.0001. 1 over 10,000. Make sense? Okay. Now, the probability that one key hashes to our given slot and the other one does not is the probability of yes times the probability of no, which is the probability of 1 over n times n minus 1 over n, which is going to be basically, think about it, the bigger n is, then n minus 1 over n approaches unity. The bigger is n, the closer n minus 1 over n approaches unity, 1. So therefore, this is going to approach 1 over n. And 1 over n was 0.01. So instead of 0.01, it's 0.0099. Almost the same. Now remember what I said. We pick the slot first, and then we see what's the probability of two of them going there. Okay, what is the probability that two keys hash to a given slot and two keys do not? Well, that would be a yes, yes, no, no. So it would be 1 over n squared times n minus 1 over n, that squared. So if n is equal to 100, this is the number I got over here. But that also means that the two keys hash and two do not means that the first two do and the last two don't. Actually, it turns out that the way for 4 keys to hash and 2 of them not to go to the same slot and 2 of them to do is to put the 2 n's anywhere you can, which is basically finding 2 slots for n in a sequence string of 4. So that's going to give us 4 choose 2. 4 choose 2. Binomial coefficient, 4 choose 2. So it's going to be 4 factorial divided by 2 factorial times 2 factorial. It's going to be 6. 1, 2, 3, 4, 5, 6. But the probability of this sequence, p, y, y, n, n, and p, y, n, p, y, n, all that, those are going to be all the same. They're all going to be the same. So therefore, the probability of 2 out of 4 keys not hashing to a slot and the other 2 hashing to that slot is going to be 6 times the probability of that, which is hopefully this, if I did it correctly. If I did my math correctly. Theory is correct. Okay, so basically, so it's important to understand that because things can happen in multiple ways, multiple sequences give you the same probabilities, it's important to understand the binomial coefficient. So if we have, so now we'll generalize it. If we generalize it, so suppose we have R keys hashing. So R keys are hashing. The probability of x of them hashing to a given address is given by probability of y to the x. That means x of them, okay? X of them are hashing, so x of them are yes, 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 followed by r minus x, no, 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 no. So if, for example, I have 6 keys, that means that r is going to be 6. The probability of 2 hashing is going to be probability of y to the second, times probability of no to the fourth, like that. But of course, that only describes the first 2 hashing correctly to the slot, and the 4 not going to the same slot. This also can happen in many other ways, and the number of ways it can happen is if we take all of the R records and we do a binomial coefficient of R, choose X. So that's how many successes we have, and that's what we get here. So sometimes we can write it like this. CRX is the combinatorial, or sometimes known as the binomial coefficient, combinatorial coefficient. RX, R choose X, is equal to R factorial divided by R minus X factorial, X factorial. Everybody's familiar with that? I think we did it already, right, for different things. Yes? We did? We did the binomial coefficient, right, for a few things.
Yes.
Okay, so nothing surprising here, right? What is this? But sometimes we write the binomial coefficient like this. I have to change my notes so this is nice and consistent. Huh? You good? Good? All right. So given a set of R keys, and R could be 6,000, could be 20, could be 5, whatever. Given a set of R keys, the probability that a given address will be chosen X times will be the probability of X will be the binomial CRX times the probability of Y to the X times the probability of no to the R minus X. Which in this case of our example is going to be 1 over n, which is the probability of yes to the x, times n minus 1 over n to the r minus x. Okay, so the probability that a single key hashes to a given slot is 1 over n under ideal circumstances of a good, or I would say excellent hashing function. One that equally targets every location. Equal probability. Now, the probability that a set of R keys hashes to a given slot is R over n. Because it's independent, right? Note that R over n is also the packing density. R over n is the packing density, because that's the number of records. And n is the number of slots, so it's the packing density. So what we have is, we have a very famous distribution called the Poisson probability. And Poisson is French for the famous mathematician Poisson. The name means fish. Yes, Poisson. Mr. Fish. And the Poisson probability has a closed form that says P of x, so the probability of x hashing to a location is going to be R over n, okay, to the x, times e to the minus r over n over x factorial. Keep in mind that r over n is our packing density. Packing density. If you have, for example, 1,000 slots and 500 records, what's your packing density? 50%. So what's 0.5? So R over n is going to be 0.5. Okay. So the probability that a given slot will have x keys hashed to it is the number of available slots or addresses, which is n, number of records to be stored, which is R, and the number of records assigned to a given address. Now, what happens here is we can simplify this. How do we get at this function? How do we get at this function? Well, this is very simple. What we're going to do is we're going to say our success rate is going to be n times a probability. So n times a probability is going to be our value lambda. So in that case, our probability is going to be lambda over n. So probability is going to be lambda over n, and what we're going to do is we're going to basically put that p value as lambda over n, and here is our p value. So p to the k, 1 minus p to the n minus k, and then the binomial coefficient of n, choose k. So this is going to be probability that we have k successes is n choose k, p to the k, 1 minus p to the n minus k. This is the binomial distribution. And the binomial distribution becomes the Poisson distribution as you take the limit. And the limit is going to be as n approaches infinity. So what we have is we have the limit as n approaches infinity, and this is nothing more than n choose k. So that's the same thing. That's the same thing as n choose k. Then p is equal to lambda over n. So p to the k is lambda over n to the k. And then this is nothing more than 1 minus p to the n minus k. So it's going to be 1 minus lambda over n to the n minus k. Whoops, sorry. Okay. So we can now take this constant out, lambda to the k over the k. There's a small mistake in here someplace where I made a mistake. I don't know what it was. N cannot come out, k can come out. So k factorial, I think this is okay here. So I think we take the k factorial out, we take the lambda to the k out because they're not a function of n. And then we have the limit of n factorial, n minus k times n to the k times 1 minus lambda over n, the n, and 1 minus lambda over n to the minus k, taking this and splitting into two factors. This to this to the minus k. So we get that. Let's just make sure everything is correct here. Yes, this is good. Okay, so now what we're going to do is we're going to take the limit of these terms as n goes to infinity, and the first term looks like this. So the first term is going to be this term right here. So as n goes to infinity, we have n factorial over k factorial, n minus k factorial. As n goes to infinity, we end up basically getting this sequence, n decreasing, 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 up to n minus k. So this is going to be up to n minus k factorial. So, and then up here we have k factors of n. So we have k factors of n decreasing, and here we have k factors of n. As n goes to infinity, all of these factors are approaching a ratio of 1 over 1, so that whole first term goes to 1. The second term here basically is the limit as n goes to infinity of this 1 minus lambda over n to the n. So this is going to be e to the minus lambda. So this is e to the minus lambda term. This is again, I'm not going to expect you to derive that from me, but I'm just showing you that as you take, what is the value of the limit of n goes to infinity of 1 plus 1 over n to the n? 1 minus 1 over n to the n as n goes to infinity. E to the minus 1. How about the limit as n goes to infinity 1 plus lambda over n to the n? E, it's going to be e. E. But if you have 1 minus something over n to the n, it's going to be e to the minus something, and that's what it is here. Okay, so that's that term. The third term is going to be, again, very, very similar. As n goes to infinity, basically what's happening is this thing just goes to, this goes to 0. So it's 1 minus 0. It's 1 to the minus k, it's going to be 1. So finally, so if you look at all those terms going to their different limits, 1 and e to the minus lambda, so what you get is basically what we have is p to the k is going to be lambda to the k, e to the minus lambda over k factorial. And that is the Poisson distribution. So the Poisson distribution is a distribution which is the binomial as n goes to infinity. Okay, so now that we know what it is, so we can now plug it in and look at our hashing function, probabilities. So assuming that we have this probability, we can now compute, we can compute the probability of 0. So probability of 0 is the probability of 0 keys hashing to a given location. Probability of 1 is the probability of 1 key hashing to a given location, 2, 3, 4, 5. Notice that as we go to higher numbers, the probability is decreasing. Now, the important thing to notice here is that the value of R over N, and R over N is our packing density. R over N is our packing density, and that is also our parameter in the Poisson distribution. Okay, so our parameter in the Poisson distribution is going to be R over N to the K, e to the minus R over N over K factorial. So So this is very important. So what happens here is, so we're just plugging it in here, and you can try it yourself. Just take this value here, take this formula here, and do probability of k is equal to 0. So you're going to get lambda to the 0, e to the minus 0 over k factorial. Okay? And you'll get the value. And the value that we have here is, in this example, is 0.368. Notice that our packing density is, I'm sorry, this is not responding nicely. It's not me, I'm not trying to give you a headache. Okay, what is the packing density here? 100%. So 100% means that we have 1,001 slots, 1,001 records. 10,000 slots, 10,000 records. The same number of records as slots. What's going to happen is that, and this is basically, look at this. This is r over n to the k, e to the minus lambda over k factorial. And the value of k is the parameter here. So this tells you that we are expecting 36.8% of the slots to have 0 records hashing to them. 0. So if you have 10,000 slots, or let's say if you have 1,000 slots, 368 of them are going to be nothing. Nothing is going to go to them. Not one record, not 2 records, not any records. We also have, when k is equal to 1, okay, we're going to have r over n to the 1, e to the minus r over n over 1 factorial, also 368. So 36.8% also will have exactly 1 record. Okay, so what that means is that if you add these two together, which is 73%, 74%, let's call it 74%. What's 1 minus 74%? 26% will have what? Slots. Will have 2 or more records going to them. That's our expectation. So our expectation is that 26% of our slots are going to have 2 or more records. Does that sound good or bad? It's not too good, because 26% is a %, of the time. It's like saying 25% of the time that I'm going to drive to work, I'm going to have a car accident. Well, that's fine. You know, as long as you're very rich and have a lot of liability and collision insurance, probably not a good idea. And you can see what's going on here. So now let's talk about how many records are going to be actually colliding. So let's suppose that we have 1,000 records. 1,000 records, which means that r is 1,000, n is 1,000. So that means the probability here, 368 slots out of 1,000 are going to have a single record, no collision. But here, we're going to have 2 records trying to get into the same slot. How many records? What's the probability of 2? 180. So 184 slots will have 2 records trying to hash to them. The good news is the first one will succeed, but the second one will fail. And since there are 184 slots, that means there are 184 records that will be colliding records. Does that make sense? So we have 184 colliding records. Now, for probability of 3, we're going to have 61 slots out of 1,000 that will have 3 records colliding to them. The first one, but the next 2 that go in the same spot, bad news. So that will be 61 times 2. So this is going to be 1 times, this is going to be 2 times 61. Then we're going to have 3 times 15. You got it.
4 times 3.
4 times 3. Is that the last one we have? And then it goes, okay, so now if we add this together, so this gives me 122, this gives me 45, this gives me 12, this gives me 184. So it's 2, 300, 350, 363.
363.
Okay, you're good. So 363 records are expected to, what percentage is that? Well, 363 divided by 1,000, 36.3%. So what can we do? Now, You might say to yourself, is this the way it's really going to happen? And the answer is no. It's not. It may happen this way. This is just some expectation. Because think about it. It's possible. You see that 0.61? So there are 61 slots that will go bang, bang, bang. So let's say it goes bang. Good. Bang. Linear. Bang. Linear. So now we got these three. And now this slot had the probability of having one record hash to it. That one is now can't go anywhere. Get the idea? If we had an overflow area, then the records expected to be P1 would have an open slot. But because we are handling our overflow in an area with a packing density of 1.0, we don't have that luxury. See what I'm saying? So it's a very interesting analysis. So the last thing I'm going to leave you with is to see, I'm not going to do the computations, but I'm going to do this. So now what I'm going to do is, let's reduce the packing density. Let's reduce the packing density to 80%. And 80%, basically what happens is that R over N is 0.8. So now what happens, of course, is now our packing density is only 80%. That means 20% of the slots are never going to be used, even if you filled it 100%. There's just going to be 20% free space. So the probability of 0 increases to 44.9%. But now if we have 1,000, if N is still 1,000, sorry, if R is still 1,000, then what's N? It's going to be, no. If R, number of records, is still 1,000, R divided by 0.8. So it's going to be 1,000 divided by 8 over 10. So it's going to be 10,000 over, what's that? Do it. 10,000 over 8, what is it? What is it? 10,250.
No, 10,000 divided by 8.
10,000 over 8.
250 will be extra.
Around how many?
Around 12,800.
Yeah.
Something.
Okay, so what it means is that now our 1,000 records require 12,080 or whatever it is slots to get that packing density. So that means that 44% of 12,080 slots are going to be now completely unused, or at least not targeted. Get the idea? So now, so the question becomes, so we should be able to calculate some interesting results here. For example, like how many slots are going to be used, how many records are actually going to collide based upon a different type of packing density. All right, so it's time for us to quit, but you have enough information so I can give you a little homework on this so you can kind of work it out and figure it all out. We're almost done. All right, have a pleasant day.